Hey folks, in lesson 17, we're going to take the idea that we developed last time about work and then turn this into something that's usable for solving dynamics problems by creating this work-energy relationship. Now the main difference that we have between lesson 17 and lesson 16 is that in lesson 16 we were considering the work done by a single force. So if you recall the hoist problems, we were only looking at the work done by the tension that was placed by the hoist on the mass. And this emphasizes the importance of this notation, in which we are very clear that it was the work done by onto particle P by this particular tension. And so what we're going to do this time is we're going to define, instead of tension T, we're now going to talk about all the forces that are acting on the particle, and instead use the total work. And so look down at the definition here, being that the total work is the energy applied to a particle P by all the forces acting on the particle along that trajectory, gamma P. And so our notation changes just slightly, in which we're now the work of all the total forces, and then the rest of it is the same. And so the important change that comes from this is actually in this term Fp, because now F sub P, if it includes all the forces acting on the particle, this means that we can insert Newton's second law, which we've already defined many times as the mass of P multiplied times the acceleration of P with respect to an inertially fixed point as observed in the inertial reference frame. And so when we apply Newton's second law and we insert this in, then we get that the total work applied to point P, so this is by all the forces, we're still giving the position of point P by our position vector, and it's along the path gamma P, is equal to the integral along the path of, and now we insert Newton's second law, so it's mass times the acceleration of point P with respect to O as observed in the inertial reference frame, dotted with our differential position dr of P with respect to O as observed in the inertial reference frame. Now this integral is no less cumbersome than what we did in the last lesson, so let's put this into a form by rearranging some terms that you've seen before, but more importantly it's in a form that's more usable. So first, let's take our acceleration and then call that the time differentiation of v of P with respect to O as observed in the inertial reference frame of, so the time differentiation of velocity, and dot that with dr P with respect to O. That's in the inertial reference frame. And so by creating this notation, we can now adjust where we want our dt. And we can move it easily underneath our dr instead of being under our dv. And so you should recognize now that what we've done is we've changed that right side to a dv multiplied times v of P with respect to O as observed in the inertial reference frame. So dot products are commutative. So this means that we now have the integral along this path of the mass multiplied times the velocity of P with respect to O as observed in the inertial reference frame, dotted with d v po as observed in the inertial reference frame. So all we've done here is we've switched this term with this term because dot products are commutative. So now we have something we can deal with because we have our integrand being m times the velocity, and then our integration variable is just velocity. So that means that our integration now is just on the velocity. So what we get is the velocity of P with respect to O as observed in the inertial reference frame. And so it's the velocity squared, which is going to be this term. It's the magnitude squared divided by 2 multiplied times mp. And then we're going to evaluate this across from from time 1 to time 2. And so this will be evaluated at the velocity as observed in the inertial reference frame of time 1 to the velocity of p with respect to O as observed in the inertial reference frame at time 2. And so as a result, we have a brand new definition for our work, in which our work is now defined as 1/2 mp, and it's going to be the magnitude of the velocity of p with respect to O at time 2 squared minus 1/2 of the mass times the magnitude of the velocity p with respect to O as observed in the inertial reference frame at time 1 squared. And this is a really cool result simply because we've taken this really kind of nasty term with work, in which we're taking the force, and then we need to find a differential path integrated along the path, and we've put this in terms of a starting velocity, so the velocity at time 1, and the magnitude of an ending velocity, or the velocity at time 2. And so we've defined the work now in a way that is completely independent of the path that it takes. And the form that we're going to most commonly use in this class is what we call the work-energy relationship. And that's where we have the kinetic energy at time 2 is equal to the kinetic energy at time 1 plus the work that's done on the system between those times. And so that's where the kinetic energy is defined as what we had just a moment ago, 1/2 mass multiplied times the magnitude of the velocity squared, or in a larger notation, it's simply the velocity dotted with the velocity at a particular time. And even though this is a familiar form to what you've seen in physics before, even what you've seen in high school, be sure that you're keeping track of where you're referencing each of these points, where you have to keep the same reference point here for calculating your kinetic energy and your work. And then in addition, we started this out by using F equals ma. In Newton's second law, we always need to be observing our acceleration and our velocity in an inertial reference frame. And so that means that as you calculate these, your velocities always need to be observed in an inertial reference frame, and you can't make these same calculations in a non-inertial reference frame. So now that you know the importance of this, simply writing 1/2 mv squared really doesn't cut it anymore. You have to be very particular and ask that question that we did the first week of class, which is, when something's moving, you always ask the question, according to whom? Another important aspect that putting work, or having this work-energy relationship in terms of velocity, what it allows us to do is now we can define the work due to an impulse. And so recall that an impulse, when we apply an impulsive force from time 1 to time 2, across a very, very small time interval, then what we're essentially doing is we're changing the velocity. And so if we're changing the velocity, you can see that this change in velocity, from time 1 to time 2, will give us what the work is done in that instantaneous change. And so this tells us that an instant change in velocity, or an instant change in speed, gives us an instant amount of work that's done on the system. So while we have that hoist example from lesson 16 fresh on our mind, let's go back and reconsider that constant velocity hoist and calculate the work done by that impulse. So recall our system in which we had a mass, and then we had a tension that was pulling the mass upward, and it went from a height of 0 to a height of h. And so we defined the work done by that hoist as the work done on mass p, or particle p, due to a tension, and it was along the path, of vertical path y, that we defined gamma p, and this was equal to the integral from 0 to h mg dy, and then we got that it was mgh. Now, we got this result because it had an initial velocity, and then to maintain that velocity, to have a constant speed, we simply needed to match the weight of the object, or the force due to gravity, with the tension that's being applied to the box or to the mass by the motor. And when we calculated the work done, we simply ignored the force on particle P due to the impulse from time 1 to time 2. That was over a small time. And this changed the velocity from 0 in what we defined as the E2 direction to a V0 also in the E2 direction. So recall that we had a V0, that was our initial speed. And so now that we have a work-energy relationship that's based on speed, we can find what the work done on that particle P due to the impulse to obtain that initial speed. So this is over that small period of time. And that's going to be equal to the kinetic energy at time 2 minus the kinetic energy at time 1. So let's write this out, where we have the work done on particle P by the impulse F from time 1 to time 2. That's over the small amount of time, so it's 1/2 m, and it's the velocity of P with respect to O as observed in the inertial reference frame at time 2 squared minus 1/2 m. It's the magnitude of the velocity of P with respect to O as observed in the inertial reference frame at time 1. And it started from rest, and because it started from rest, then the magnitude of the velocity at time 1 before the impulse is 0, and the magnitude at time 2 is V0. So the work due to the impulse F time 1 to time 2 is equal to 1/2 m V0 squared. So now this actually changes things. So for our constant velocity hoist, the work onto P due to the tension along this path is going to be equal to mgh during the path from 0 to h, but then we need to add the work due to the impulse that got it moving in the first place, which is 1/2 m V0 squared. And so this is our constant velocity hoist. And let's compare that now to the work done by the jerk hoist. The work done by the jerk hoist, we said, was mgh plus mhb over 2. And recall that b was a constant that told us how the force changed because it started high and went lower throughout the stroke from 0 to h. And so now the comparison done by the tension in the constant velocity hoist versus the tension done by the jerk hoist is not quite as stark, because we have this common term mgh in both of them, and the only differences are going to be in these extra terms. And so when we compare them, we see that the constant velocity hoist still does less work, but only when our initial velocity, our initial speed done by the impulse, is less than the square root of b times h. And that's going to be the accurate comparison between what's done by the tension. And so, main point here is, now that we have this tool, this work-energy relationship, putting this in terms of velocity, this really makes these calculations much easier to do in terms of calculating work, but also understanding how the system velocity or the system speed changes from a time 1 to a time 2, or from a point 1 to a point 2 along that path. Let's do an example where we apply this work energy principle. So what we have is this ball bearing sitting on top of this curve, and then it starts from rest at position 1 and slides down the smooth surface of the cylinder to position 2. And so we have dimensions here. We'll work the problem dimensionless and then add in the dimensions later. And then we want to find the total work done on the pellet as it slides, or the ball bearing rather, as it slides from position 1 to position 2, and then also the speed at position 2. So like all problems, we're going to start out by defining our reference frames. And so we have an inertial reference frame with E1, E2, and E3, where E1 is defined along OP when theta is equal to 0, or equal to 90. E3 is into the page, and then E2 is E3 crossed with E1. Then let's apply a path frame to this problem. And so reference frame B is our path frame, in which we have E sub t, which is tangential to the path or along the velocity of p with respect to O, as observed in the inertial reference frame. And then we have E sub n, which is perpendicular to E sub t and pointing into the radius of curvature, or inside the curve. And then E sub b, which is Et crossed with E sub n. This path is a really well-defined path, so we can create a relationship or transformation between these variables. So we'll draw our E1, E2, and then E sub t, and E sub n. We have an angle theta between those vectors. And so we get the relationship where E sub t is equal to cosine theta E sub 1 plus sine theta E sub 2, and then E sub n is equal to minus sine theta E sub 1 plus cosine theta E sub 2, which then gives us the transformation table: E sub t, E sub n, E sub 1, E sub 2, which we have cosine theta, sine theta, negative sine theta, cosine theta. Alright, now we're ready to work this problem. So the first thing we want to do is we want to find the work done on point P from theta is equal to 0 to theta is equal to 30. So recall that one of the forms of work that we could use is the work on P, and we're finding the total work is going to be, so this is R, P with respect to O, along the path, and let's use the path S. So this would be the integral of all the forces along that path S, dotted with the ET direction, since we're using our path frame, ds. And ds, our path S, is simply defined as this arc length. So S would be equal to r theta. And so if S is equal to r theta, then ds is equal to r d theta. Alright, let's take care of our term, our total force. And so our total force, we need to draw a free body diagram. So our free body diagram of our particle along this path is going to be mg, and that's in the E2 direction. And then we have a normal force, and that's a normal force in the negative En direction. And so our force F sub P, this is our total force, is equal to negative N in the En direction plus mg in the E2 direction. Now we need to convert this into some way, and so because we're going to be taking a dot product with E sub t, let's convert everything that we have here into path coordinates. Our normal force is already in path coordinates, so let's convert our gravity into our path coordinates. And so to do that, write this out, we're going to use our transformation table. Our force is negative N in the En direction, plus, and it'll be mg in the sine theta Et direction, and then plus mg cosine theta E sub n. Let's plug all this into our definition of our work using the path frame, and we'll get that the total work, and this will be from theta 1 to theta 2, point 1 to point 2, is equal to the integral, and this is negative n in the en direction, plus mg sine theta in the et direction, plus mg cosine theta in the en direction. We're dotting this entire piece with e sub t, and then for our ds, we said that ds is equal to r d theta, so r d theta, and then our integration bounds are going to be from theta 1, theta at point 1, to theta at point 2. So our total work, after doing the dot product, is going to be the integral from theta 1 to theta 2 of et dotted with the inside of this for our force is only going to be mg sine theta, and then we have an r d theta, and when we take the integral we get negative mgr cosine theta, and it's evaluated using the fundamental theorem of calculus, theta 1 to theta 2, and finally given us the quantity where our total work from theta 1 to theta 2 is equal to negative mgr of cosine theta 2 minus 1. Oops, got ahead of myself. Cosine theta 2 minus cosine theta 1. So now let's apply the conditions that we were given to find our total work. So it's not from theta 1 to theta 2 anymore, it's from 0 degrees to 30 degrees down the slope. And this is going to be equal to, so it's minus, and then we have 0.2 kilograms multiplied times 9.81 meters per second squared, multiplied times 0.8 meters, and then this will be cosine 30 degrees minus cosine of 0, and cosine of 0 is 1. And then we get that the total work done from 0 degrees to 30 degrees on this particle, this is of point P, is equal to 0.263 joules. Alright, now let's use the work energy relationship to find the speed of the ball bearing at time 2. So we'll start by writing the definition of our work energy relationship, which is the kinetic energy at time 2 is equal to the kinetic energy at time 1 of the particle plus the work done on the particle, and this is the total work from time 1 to time 2. Let's write this out in our longer form, which is 1/2, and it's the magnitude, the velocity, p with respect to O as observed in the inertial reference frame at time 2 squared is equal to 1/2 the mass times the magnitude, the velocity of p with respect to O in the inertial reference frame at time 1 squared plus the work, and it's the total work, so due to all the total forces, time 1 to time 2. And so let's take a look and see what we know and what we don't know. So we know this. We just calculated this. And we also know the velocity at time 2. And so we know that the velocity, we know the velocity at time 1. The velocity at time 1 is equal to 0. So that means that the kinetic energy at time 1 is 0. And so what we're solving for now is the velocity, or the magnitude of the velocity, at time 2. And so we get 1/2 and then 0.2 kilograms multiplied times v of p with respect to O as observed in the inertial reference frame at time 2, which is our speed at time 2 squared. And this is equal to 0 because there is no speed at time 1. And then we'll add to this the work that we just calculated, which is 0.263 joules. And so we get from this that the magnitude of the velocity of p with respect to O at time 2, as observed in the inertial reference frame, is equal to the square root of 2 times 0.263 divided by 0.2. And from this will give us 1.62 meters per second. And so our speed at time 2 is 1.62 meters per second. Now, one quick word of caution is that as you're going through this, it's not terribly intuitive to be converting between joules, and here we have the magnitude meters per second, and then kilograms, or meters per second, and then that's a squared term, and then kilograms. So it's really important that you take your time writing out all these quantities, because this is a work and an energy relationship. And so checking your units can be difficult at the ends of problems, even though that's oftentimes the best way to go about doing this. Alright, that wraps this up, and I'll see you in class.